first speaker is Hao Ni, who's from the Maths department at University College London. She's also affiliated with the Allen Institute. Without further ado, I will get started. Thank you very much for the presentation and introduction. It's my first opportunity to talk about our recent work, the characteristic function based on GAN model or simulating synthetic time series. So the main objective of our work is to improve the quality of the GAN model for time series generation from the perspective of the characteristic function of the measures of the pathways. And in this part, I will talk about the methodology and the empirical validation of our proposed method, the PCF-GAN. Additionally, I will also present the application of the PCF-GAN to the Levy area generation, which is instrumental for accelerating the SD problem. The generative adversarial network GANs are powerful tools for simulating synthetic data. In particular, the static image data. So the GAN model are often composed with the two parts, the generator and the discriminator. The generator aims to map the pre-specified the noise vector to the target fake distribution, while the discriminator is used to maximize the discrepancy between the smooth distribution and the fake distribution as much as possible. And both generators and the discriminator are often parameterized by the network and characterized by the corresponding model parameter. Then the task of learning the generator boils down to limited to the main aspect. So more specifically, with the discriminator, we like to optimize the model parameters of the generator to minimize the distance. While when we fix a generator, we will optimize the model parameters of the discriminator to maximize the distance. And we can do this optimization in the alternative way. And when we reach the equilibrium, we have the generator to simulate the fake data. And here you can see that by the nature of this min-max game, the GAN training is often computationally expensive, and it requires quite a lot of expertise to make the actually converge. And for the time series data, the GAN training might be even harder due to the potential high dimensionality and the complex spatial temporal structure of the time series data. And I'll mention that in comparison with the static image data generation, the evaluation framework of the time series data generation will be even much harder and less well established. So to this end, we would like to improve the quality of the GAN model by innovating the discriminator. And our approach is to incorporate the more mathematical principled description of the distribution induced by time series. And we will leverage the rapid theory, a branch of the stochastic analysis, to make the discriminator more effective for the time series data. For people who don't know much about the RAPAS before, let me quickly give a very brief introduction. So the RAPAS theory could be viewed as a generalization of the control differential equation driven by a very rough signal, even rougher than semi-martingale. And the one core objective of the object in the RAPAS theory is so-called the signature of the Intuitively, we could regard the signature of the past as the non-cognitive polynomials on the past space, and it serves as the universal and characteristic feature representation of the past, and also the discrete time series. So in our previous work, by utilizing the signature and the feature representation, we approximated the W1 distance on the measures of the path space and reduce the min max again to the supervised learning. So it can improve the training efficiency and stability and achieving the satisfactory result on some data depth. However, this CW-GAN model has its own bottleneck that is caused by the curse of the dimensionality of the high path dimension, as well as the degree of the complicated signature. So to overcome this bottleneck, we propose to use the alternative feature representation of the time series supported the unitary feature of the path. And so on the high level, the unitary feature of the path plays a role as a generating function of the signatures, which offer the method of dimension reduction. And the resulting GAN model, PCF-GAN, is much scalable for the high dimensional time series. Throughout this talk, I will focus on the continuous path space. In practice, we often observe the discrete time series rather than actually continuous time series. However, we can embed discrete time series to the continuous path space. By doing so, it offers the unified treatment for the time series with actual irregular control and also variable depths. And such, and also this representation, if we regard, and also this this view of viewing the discrete time series as the paths is more well suited to the high frequency string data. Then the key question for designing the good discriminator from the time series generation actually boils down to two key questions. The first one is how can we represent the measures on the path space, and the second is how to quantify the discrepancy between two distributions on the path space. And in this talk, for the ease of the discussion, I restricted the path space to be the set of all the time augmented paths of the bounded one variation, and the starting point is the origin. Before diving into the PCF-GAN, I'd like to give a quick recap about the characteristic function-based GAN model for the finite dimensional random variable. So here that X denote RD value in the variable, then the characteristic function is defined in the standard way. That is map the RD value vector lambda to the expectation of exponential of I times the inner product of lambda and x. So characteristic function has the nice mathematical properties. That is, it always exists and it has a uniqueness. So the characteristic function can determine the law of x. In comparison to the movements, the movement can determine the law, but this implies the regularity condition. The decay rate of the movements need to fast down. And also the characteristic function has a uniformly boundedness. And this property is actually quite useful for the GAN training. If we think about the W-GAN, we need to add the gradient penalty term, gradient constraint in the loss function. However, for the characteristic function, because of this uniformly boundedness, we don't actually need to impose additional gradient constraint. And now I'd like to introduce the characteristic function distance, CFD for short, completed by the and the co-author in 2020. So given x and y, the two RT-valued random variable, and then we can define the CFD distance between x and y associated with the any value of random variable capital gamma by this formula. So that is the square of the CFD distance is given by the expectation of the L2 norm of the difference between the characteristic function of x and the characteristic of y evaluated as this random variable gamma.
And Hua et al. Ansari, I understand, and the other names, yeah.
I need to.
You said Ansari et al., Ansari et al., and Hua et al. Just to understand, you know, yes. I want to know the authors, you know.
No, I understand.
Okay, good.
Scarlett, Johansson.
Representing. Yeah, I'm sorry.
Sorry. Okay.
All the authors' names.
Okay, thank you. Stupid question.
Yeah, so this expectation is taken under the measure of this capital gamma. So basically, we have the two characteristic function. We calculated the difference and taking the L2 norm, and we integrate it against this measure of gamma. So it's not difficult to prove that if this capital gamma has a full support, then this is CFD distance between x and y equals to 0 if they are always equal to the same, and it also equals the uniformly boundedness. So how can we use this CFD distance for the GAN training? The idea is actually quite natural. So we will use the empirical distribution with the finite sample lambda collection of lambda I to approximate this capital gamma in a non-parametric way. Then the corresponding empirical CFD distance would be reduced by this average formula. So we would treat the collection of lambda I as the model parameters to learn from the data. So given x and y, the tree and the big data, we will optimize the lambda I to maximize the distance. And when we fix the lambda I, we will optimize the model parameters of the generator to minimize this distance. So we are in the training. For our case, we would like to extend this work for the measures of the pathways. Then the key question is how can we extend this exponential map when x is a path value variable? So actually the raw passage really provides an answer to this question. So before introducing the definition of unitary feature of the path, which is the natural extension for this exponential function, I need to introduce the following definition. So unitary matrix group of degree m, denoted by this capital UM, is the set of the complex valued matrices such that A conjugate times A equals to A times A conjugate equals to identity map, and its D algebra denoted by this small um is the set of all the independent matrices. So here I want to emphasize that the Lie algebra is an actual so that the matrix Lie group is not. So now let me give you the full definition of the unitary feature of the path. So let's first fix the integer m, which is the matrix order, and let x denote the path of the bounded one variation. And this capital M is a linear map, which maps from the RD onto the Lie algebra UM. The unitary feature of x associated with this linear map M is denoted by this curly UM of x, and it is the solution. That is the capital YT, Y capital T, and here YT is the solution to this linear control differential equation. So here the multiplication is understood as a group operation. So it's here in this particular case, it's the matrix multiplication. And the initial point y0 is the identity map. And it's easy to see that the solution YT lives on the unitary group UM, because the right hand side of this linear control equation is actually within the tangent space of the unitary group at the reference point YT. And we call the map from any linear map M to the corresponding unitary feature as a unitary feature of X of order M. And it has been proved in Chernev and the Lines paper that the unitary feature of X of all possible order determines the path uniquely for any path X in this curly X path space. And in fact, that this unitary feature of the path could be extended to, it's a special case of the Cat development. So the general path development feature is defined in the similar way, but it could be applied to the general matrix Lie group, not just only the unitary matrix Lie group. This path development in the raw path literature is a useful mathematical tool to understand the property of the signature and expected signature. And more recently, we use the path development layer as the new sequence to sequence layer for machine learning purposes. And it has the good analogy with the recurrent neural network and also the continuous time series model. So let's have a closer look at the symmetry feature of the path. So let's consider the linear path. So X here is a linear path, and the unitary feature of X on the associated with the linear map M actually can be solved explicitly. So it's nothing else but matrix potential of this linear map X on the increment of X from 0 to T. And how does it connect with the classical case? So here, if we consider X is a linear path and choose M equals to 1, then this the algebra of the unitary group is reduced to the set of all the imaginary numbers. And so for every linear map M, we actually can identify the constant vector lambda M such that it could be this linear map M could be rewritten as the I times the inner product of lambda M and Y. Here you can see that the unitary feature of order 1 is actually just this exponential map, which is used in the classical characteristic function. And moreover, this unitary development has a nice multiplicative property. So if we have the two paths X and Y of bounded one variation, then the unitary feature of the concatenation of the X and Y is the product of the unitary feature of X and the unitary feature of Y. And this property allows us to actually compute the unitary feature of the piecewise linear paths. And the following, I like to provide you with some intuition why the unitary feature can capture the essential information of the sequential order of the events inherited in the time series. So here, if we start from the piecewise linear path, the unitary feature of this path is actually can be regarded in calculating in this way. So we first take the difference to get the linear segments increment at each time t, so delta xt. And for each linear segment, we use this matrix exponential composed with a linear map to map the eigenvalued increment to the matrix in the unitary group. Then we multiply the unitary matrix for each linear segment to get the unitary feature of the entire path. So here for the linear segments, and we can easily see that this unitary feature can characterize this RD value vector if we choose the matrix order high enough. And then the matrix multiplication is not limited. And this property helps us to use a unitary feature which can preserve the order of the linear path segments. So if we change the order of the linear segments in our data, then the resulting unitary feature might be different for certain linear map. And also, because of this group structure, then at each link, so the unitary feature of each linear piece lives in the unitary group, multiplied together to do the group, and also it helps with the uniform boundedness. So yeah, that's the intuitive justification about why this unitary feature can characterize the information.
Can I ask a very basic, naive question? Can we go back? Sorry, because I didn't catch the detail. No, the next slide, which is very important. Thank you very much. This is a fantastic illustration, but I want to understand this key sentence that says it preserves the order of the linear path segment. What order is this?
Oh, okay. So I should write the orders of the linear path segments of delta x, t, and m from 1 to capital M. So here we have the delta.
The sequential order, you mean?
I should do all.
Thank you.
So with this unitary feature, I'd like to explain to you a bit more how we can use that as the layer for the sequential data learning. So here, note that the linear, so the map M is linear. So it can be fully characterized by its linear coefficient theta, and this theta m is the model parameters of this unitary development layer. And the unitary development layer has an input that is a path of the piecewise linear path. And the theta m is the model parameter, and it outputs the unitary feature of the x, which is the group element in capital UM. And because the output of the development takes the value in the group, when we do the when we design the algorithm for the backwardation, we need to take care of this group value output. So here we use the method called the trivialization, which is approach to solve the optimization of the matrix of the Lie group, and we succeed in implementing the backwardation of the passive development layer. So to make it simple, so we have the software to implement the development layer. To put it simple, the procedure is we have the discrete time series data, then we embed it into the continuous path space by the linear interpolation. Then for the given the model parameters that we output the unitary matrix valued output. Okay.
There. Sorry, go back. Yeah, okay. Where is theta in the unitary matrix? Where is the parameter?
So the linear map is parameterized by its linear coefficients.
Okay.
That's the theta here. So what I'm saying is that given theta, that's the coefficient, linear coefficient, then it induces the corresponding linear map. And beta, then we calculate the unitary feature.
Yeah, but you do the optimization in terms of theta.
Yes.
Yes.
Yeah.
Where exactly? This is what I want to understand here. right? Because you say the M theta and then obtain the unitary matrix, right? So you do the back propagation. Can you say a couple of sentences to explain this kind of procedure again?
Okay.
With
so-
this example. So we are in we have the path using the linear segments, right? But now ideally theta will not be fixed, but it will be some parameter. And then how do I use the back propagation to solve the optimization problem there?
So in this illustration, I didn't include the loss function. So we should have the loss function, which takes this unitary feature as a input. And then the optimal linear coefficient theta is obtained by minimizing this loss function. So here I illustrate how we evaluate the unitary feature. So this is a forward evaluation of the this unitary development layer. But to do the back propagation, we actually should have first have the loss function and calculate the gradient to allow this SGD numerical questioning.
So, but this loss function then, is it non-convex in theta?
May not be in general.
Is that loss function in your GAN is like minimax like loss function? The GAN?
In GAN, yes, that's what I'm going to talk about later.
Sorry, one more thing. So why the unitary matrix dimension is 3 by 3?
Oh, so this is an example.
Okay, so that's a dimension that you can, like the user can.
Yeah, the user can choose whatever the matrix order that they want. Yeah.
Can you specify like how we should like define those like the dimension of the unitary matrix?
Sorry.
I mean, like what is a good dimension for the unitary like matrix?
You mean?
I mean, here is 3 by 3, but you could do by 2 by 2, right?
Yeah, so in our numerical experiments, we can even choose this like with order like 30. But the good choice of the matrix order for the numerical experiment should be chosen based on the numerical performance.
Okay.
Yeah.
So it's like hyperparameter tuning.
Yes. So here what I want to say is that the unitary development layer implement can be used as a general layer for the time series. So the loss function could be the one I show you later about the task characteristic function based distance, but I mean it can be used for as a loss function as well in general. So as now we are ready to introduce the definition of the adversarial function. So let's consider X to be the random variable taking value of the bounded one variable. Then plus the characteristic function of the order now is defined as the map, which map from this linear map to the expectation of the unitary feature of X, and this expectation is taken under the measure of the X. And it and it's not difficult to show that this PCF function of X exists, and also it has a uniqueness. The PCF of all order can characterize the law of X, and it enjoys the uniformly boundedness. It's like the characteristic function for the undevalued random variable. Moreover, that because of the inclusion of the category matrices. So here we actually can show that if we have two different passive distribution X and Y, and they are different, there we can find the sufficiently large M such that the PCF of X of order M is not the same as that of Y. We don't need to consider the PCF of X of all the order from 1 to M, which is near to the order M. And to use the PCF to design the score to quantify the distance between the two path boundaries to the norm on the metric space. So here we use a different norm. I will introduce the corresponding path characteristic function distance. It's very similar for the finite dimension space. So given two stochastic process x and y, then we have the path characteristic function of x and y of order m respectively. And here we have this curly m is the probability measure on this linear master space. And the PCFD distance of x and y associated with this curly m is defined as the expectation of the L2 difference between PCF of x and y. And this expectation is taken under the measure of this curly m. And similar to the RD value in the finite dimensional case, we can establish the desirable properties of such a PCFD distance, which are useful for the GANs. That is the proportion of the force, uniformly boundedness, and the Lipschitz continuity. So this statement, this theorem on the Lipschitz continuity states that if we have the generator G here, it's Lipschitz in the modifier theta, and then we consider the PCFD distance of this fixed distribution induced by G theta of x, and also another distribution, true distribution x. Then this associated with the linear map. Then this is a function with respect to theta, and given the regularity condition, this PCFD distance is the Lipschitz in terms of theta, which is the justification for the gradient-based method for optimizing the generator. Similar to before, where we will use the empirical measure to approximate this curly the random by the finite set of the samples. It's a collection of MI, and this collection of MI are the model parameters associated with this PCF distance, and need to be learned from the data. So here is the illustration about how we calculate the PCF of the stochastic that empirically. So for each samples drawn from X, we calculate the corresponding unitary feature associated with this linear map theta, and we simply with the average of those unitary feature to get the empirical estimation of this of the X. So now we are ready to show the vanilla version of the PCF-GAN. So the goal is to build the generator such that its distribution could be close to the distribution of the real-time theory. So let me first explain the generator. So the generator could be quite generous. So here for simplicity, we consider the noise vector that is E values time series, and the increment of EN is the normal distribution with 0 in and the variance of 1 over 28. And the generator is the model which maps the E-dimensional time series to D-dimensional time series. And here the capital Y denotes the induced fixed distribution by the generator G theta G. And so this generator architecture, as long as we have a certain sequence to sequence neural network and use in our PCF-GAN framework. And the corresponding then the discriminator, as we can imagine that we will use a PCF-D distance between x and y. And now we can do the min-max training to find the optimal parameters of the generator as well as the discriminator. And to enhance the capacity of the PCF-GAN, especially for the high-dimensional time series case, we incorporate the auto-encoder into our PCF-GAN. The idea is very simple. So instead of to match the distribution of the true and fake time series directly, we learn an efficient embedding from the data, and we match the embedding of the true and the fake data. And there is one important thing about the embedding that is not the RRC. Otherwise, we may lose the important information about the time series distribution. So here we after there are 45 laws. So the generator lot is defined as a PCF-D of the embedding of the true and the fake data. And we will also use the two additional laws, that is the reconstruction laws and the regularization laws, to enforce this inductivity of the embedding. And here the embedding capital F and the generator G serve as the pseudo inverse of each other. Therefore, in the ideal case, F composed with B should be close to the identity. And this reconstruction loss is used to enforce the sample reconstruction. And for the regularization loss, so if we do have the good embedding, then because this F is an inverse of pseudo inverse of capital G, that means the embedding of the true distribution should be close to the noise factor distribution. And we will use this regularization loss to enforce this property. For the GAN training procedure is outlined here. So to train the generator, we minimize the generator loss. And to train the discriminator, now we have the two sets of the model parameters for the discriminator. One is the model parameter for the embedding, while the other is a PCF-D the model parameter. So to train the embedding, we consider this loss function by adding the penalty term to enforce the inductivity of the embedding. While for the to train the model parameter of the PCF-D, we maximize the corresponding generator loss and the regularization loss respectively. Okay, so in the following, I'd like to show you the numerical breakdown. So we benchmark our model of the four different time series data. That is a probability model to reflect our policy data as well as the unstudied data. And then here you can see from the summary table about the perspective of those four data sets. They have quite different pieces of the set. So the path dimension to rank from 2 to 14, and the time dimension to be as high as 200. To benchmark our model, we choose the GAN model specific for the time series generation. That is core GAN, RC GAN, and time GAN. And the only time GAN have the path reconstruct functionality as our PCF-GAN. And to assess the quality of the synthetic time series generation, we consider the three different types of the test metrics. That is a discriminator score. So we train a post-quality classifier to distinguish true and fake data. And the lower accuracy of the classifier, the better quality of the synthetic data generation. The second test matrix is predictive score. So the idea is that the fake data should be used as it can be used as a surrogate data to the real data. So the task we consider is so we predict the later part of the time series given the first half part time series information. So we do this regression on the generated data and the real data respectively, and we use the real data for testing. So the closer performance between those two regression, the better quality. We also include the CMMD, that is a generic metrics for the distribution of the path space to assess the performance. So here there are the sample plot comparison of all the models. And on this is a plot to show the sample plot of the real-time series. And you can see that PCF-GAN and PCF-GAN gives a pretty good result. However, when we have the high-dimensional time series, the visual validation would not be possible. So here is a summary table for of all the models across different data sets. And so I see that the PCF-GAN outperform the other methods consistently. And in terms of the reconstruction functionality, our model outperforms the time GAN. So I want to highlight the past reconstruction functionality of the our PCF-GAN. So here the leftmost column shows a path from the real data. And given the embedding and the trained generator, we are able to reconstruct the path. And if you look at the reconstruction performance by our model at the time GAN, our model seems to better capture the order of the events in the time series. And those two additional loss, recovery loss and the regularization loss, are also quite useful in terms of the monitoring the GAN training. Almost time, but okay, so I will be quick. So I'd like to use the following few minutes to talk about the application of the PCF-GAN for even the non-time series data. So in this case, the goal is to use the conditional generator to simulate the samples such that its distribution is close to the conditional law of the Levy area given the Brownian motion increments at time 1. So we build the Levy GAN to solve this task. The generator is the conditional generator. So the taking the Brownian motion increment and the noise factor, we generate the samples. And the discriminator here, what we do is we consider the joint distribution of Brownian motion and the Levy area at time 1. And we embed it into the linear path and use the CF discriminator for the training. So we consider the two baselines, that is the Foster's method and the Davis method, which are the moment method for the Levy area generation, and we also consider various evaluation measures to assess the performance of the Levy area generation. And empirically, we can show that our Levy model achieves a very good empirical results. And also this synthetic Levy area generation, it is also useful for the high order SDE solver. And this is illustrated by this numerical example of estimating the solution of the long stochastic volatility model. So here, our method is we use the market level polynomial with the big area generator, and you can see that our proposed method has a better convergence rate empirically. So it's demonstrates the promising direction for using the synthetic Levy area generation for the SDE approximation. So in conclusion, I this view that the past characteristic function is a useful physical representation for the law of the past value of the running environment, and the corresponding PCF distance has a characteristic uniform boundedness and the differentiability with more parameters, and it can be used as a generic metric to quantify the discrepancy between two past value running variable. And by incorporating the auto-encoder, the PCF-GAN is scalable for learning the distribution of the high-dimensional time series data. And also this auto-encoder structure enables us to reconstruct the past from the embedding. And it comes on the physical work. We explore the quantum representation of the PCF distance. So the PCF distance can be also viewed as the MMD distance. And it would be interesting to explore the theoretical more with the type of